Hi students, today we are going to study Gauss's theorem and the properties of conductors. We have studied so much about electric field lines, about electric potential, about the electric field because of charged bodies. Gauss's theorem is a special law that helps us calculate the electric field because of any charged body very easily. So what is this Gauss's law? And there is a quantity called flux that is important in using Gauss's law. So what is this flux? We're going to study all these things in this chapter. We're also going to study some fascinating properties of conductors. The actual conductors that you see in your daily life. For example, did you know that charge can only be distributed on the surface of a conductor? Why is that so? We'll study all these properties. Let's proceed and first study about electric flux. What on earth is electric flux and where did this quantity come from? The word flux basically relates to flow rate. So if you have water flowing through this small opening here, like this, in that case the flux of water will be the flow rate of water through this opening. So the word flux basically refers to the flow rate. When we talk about electric flux, we are basically talking about the flow of the electric field. How much electric field is flowing through an area? Well, roughly that's the electric flux. The electric flux is proportional to the number of field lines passing through a given area. You see, when you look at the field lines, don't you get a feel that they represent the flowing of the electric field? So the number of electric field lines passing through a given area, the electric flux is proportional to that quantity, because the electric field lines roughly represent the flowing property of the electric field, isn't it? How much electric field is passing through a certain area, that can be calculated using electric field lines. Now, we had earlier calculated that the number of field lines is proportional to integral E dot ds, where E is the electric field vector and ds is the area vector, through which we are calculating the number of field lines. We had derived this expression, long ago when we had first discussed, the properties of electric field and what an electric field was. Now, since the number of field lines is proportional to integral E dot ds, and since the electric flux is proportional to the number of field lines passing through a given area, therefore, the final formula of the electric flux is integral E dot ds. So the electric flux is basically, the dot product of the electric field vector and the area vector. Understood? Initially this might seem a bit complicated and you might not be able to physically visualize what electric flux means. But as we proceed in this chapter, you'll definitely get a feel of electric flux. The physical visualization of the flux because of this point charge passing through this elliptical area that you see on your screen is the number of field lines, that are passing through this area. So as you can see, the electric flux is more, for the same area near the point charge. For example, the electric flux is more through this area, than this area, because a greater number of field lines pass through this area. So the physical visualization of electric flux is basically the number of electric field lines passing through a given area. Roughly, electric flux is the amount of electric field flowing through any area. Electric flux is a scalar quantity. Remember, we just written that electric flux is integral E dot ds, the dot product of the electric field vector and the area vector. Well, clearly, dot products are all scalar quantities. So, electric flux is a scalar quantity. It doesn't have any direction. An important law that uses the electric flux and that we're definitely going to study in detail is Gauss's theorem. Gauss's theorem states that the total electric flux bound by a closed surface is directly proportional to the amount of charge enclosed by the closed surface, and the proportionality constant is 1 by epsilon naught. Did you understand the meaning of the statement? What Gauss's law was saying is that if you have any surface, let's say a surface like this, then the net electric flux, bound by this closed surface, that is, approximately the number of field lines that are coming out of this closed surface, is proportional to the amount of charge enclosed by this closed surface, Q. And it is not just proportional, it is actually equal to 1 by epsilon naught times the charge enclosed by this closed surface. So if I have a surface like this here, and it has a charge Q by 2, then the net flux passing through the entire area of this closed surface will be equal to 1 by epsilon naught into the charge enclosed, that is 1 by epsilon naught into Q by 2. Another way of writing Gauss's law is that net flux, which is the same as integral E dot ds, is Q enclosed divided by epsilon naught. Now why are we saying all this? Like, where did Gauss's theorem come from? You see, we already know that if you draw a closed surface like this around a point charge, then the number of field lines passing through this area of the enclosing surface is clearly proportional to the charge enclosed. We had earlier in our discussion of field lines discussed that the number of field lines coming out of any charge are proportional to the magnitude of the charge. So the more the charge, the more the number of field lines coming out. So if you take any closed area, then obviously the number of field lines passing through the area will clearly be proportional to the magnitude of the charge enclosed. Now since electric flux is proportional to the number of field lines passing through an area, therefore electric flux is also proportional to the charge enclosed by the area. And roughly you can understand that the net electric field flowing out from any closed area is clearly proportional to the net charge that is creating the electric field in the first place. Isn't it? The more the charge, the more the electric field that will flow out from the closed area. Isn't it? So using simple logic like that, you can understand the basis for Gauss's theorem. So if I take any area like this, or if I take any area like this, the net flux flowing through this area will only depend on the net charge enclosed by the area. So this area and this area will both have the same flux flowing through them. Why? Because the net charge enclosed by both these areas is the same, isn't it? And according to Gauss's theorem, the net flux passing through an area is simply equal to Q by epsilon naught, the net charge enclosed divided by epsilon naught. So that was the statement of Gauss's theorem. Gauss's theorem is extremely useful in calculating the values of electric fields of a point charge, or of a straight line, or of a sheet of charge. Remember, we had earlier used elements, in a sheet of charge. We had used elements to calculate the electric field because of a disk of charge. But we don't need to do all that. We can simply use Gauss's theorem. Let's see how Gauss's theorem makes determining the electric field easier. Now let us first try to calculate the electric field near a point charge using Gauss's theorem. How do we do that? Well, we take a point charge Q, and we take a spherical area enclosing this point charge Q, correct? Now we see that if we take this spherical surface around the point charge Q, the electric field because of the point charge will be directed radially outwards, perpendicular to the surface, isn't it? So the electric field here will be in this direction, perpendicular to the spherical surface. It will be here in this direction, perpendicular to the spherical surface. So basically, if you consider the area vector at any particular point, if you consider this small elemental area here, anywhere on this surface, in that case the area vector at every point will actually be parallel to the electric field vector, isn't it? The area vector is taken perpendicular to the surface area, so clearly it will be parallel to the electric field at any point. So if you consider any small elemental area, let's just take any area here. In that case, the elemental flux passing through this area will be E dot ds, isn't it? Now we know that integral E dot ds is Q by epsilon naught according to Gauss's law. But since the electric field is constant for every point on this Gaussian surface, this surface that we took, surrounding the charge q is called the Gaussian surface. So since for every point on this Gaussian surface, the electric field is constant, because the electric field because of a point charge varies radially. It's definitely constant at every point on this Gaussian surface. And the angle it forms with the area vector is also constant. It is 0. So we can clearly say that E into integral ds, that is E into S, is q by epsilon naught, isn't it? And when we say that, the surface area of this Gaussian surface is 4 pi r square, if you assume, that we have taken this Gaussian surface at a distance r from the point charge. So E into 4 pi r square is q by epsilon naught. The net electric field because of a point charge, at any distance r from it, is q by 4 pi epsilon naught r square. And we know that this is the expression for the electric field because of a point charge. So thus we have derived the electric field expression for a point charge using Gauss's law. Why did we consider, only a spherical Gaussian surface in this case? After all, Gauss's law states that the net flux passing through any surface is q by epsilon naught. So why didn't we take, a surface like this or a surface like this? We could have done that. We didn't do that because it was easy to calculate the electric field by taking a spherical Gaussian surface here. You see, we generally take a Gaussian surface such that, the electric field is constant throughout this Gaussian surface, because, otherwise we'd have to calculate the elemental area and the electric field for each elemental area and then integrate throughout the area. But if the electric field is constant, we can clearly replace integral E dot ds by E into S, isn't it? Similarly, we try to make sure that our surface is such that the electric field generally makes an angle 0 degrees with the area vector, because otherwise, had the electric field made an angle theta with the area vector, we would have written E into S into cos theta, isn't it? But since the electric field makes an angle 0 with the area vector, we just wrote E into S. So we take, the kind of surface that will help us calculate the electric field very easily. That is the reason we took a spherical Gaussian surface in this case, isn't it? Let's now move on and find out other electric field. So this straight line of charge has charge per unit length lambda. Now to calculate the electric field near the straight line, let us consider a Gaussian surface in the shape of a cylinder, as you can see in this figure. The length of this cylinder is L. Now we know that according to Gauss's law, the net flux enclosed by this cylinder is q by epsilon naught. Now we know that since this is a straight line of charge, so by symmetry, the electric field because of the straight line of charge will be in the radial direction like this, like this, like this, like this, like this, isn't it? When the surface of the cylinder is curved, the electric field will be like this and the area vector will be like this. So at every point, on the curved cylinder, the electric field and the area vector will be parallel to each other, isn't it? Also, the electric field will be constant, at every point on the surface of the cylinder. That is because all points on the surface of the cylinder are equidistant from the straight line of charge. So every point on the surface of the cylinder will have the same magnitude of electric field, and this electric field will always be parallel to the area vector on the surface of the cylinder. However, when you consider the two sides of the cylinder, you can see that the area vector for these two sides will be perpendicular to the electric field because of the straight line of charge, isn't it? After all, the electric field will always be directed, perpendicular to the straight line of charge, while the area vector on the side of the cylinder, here and here, is parallel to the straight line of charge. What this means is that when you apply Gauss's law for this cylindrical Gaussian surface, and when you say that integral E dot ds is q by epsilon naught, in that case, the net flux passing through these two surfaces, the sides of the cylinder, will be 0, isn't it? After all, E and ds will be perpendicular for these two sides. For the curved surface, however, the net flux will not be 0. because the electric field is parallel to the area vector. So just as in the previous case of a point charge, in this case also we will say that E into the Gaussian surface's area is q by epsilon naught. That's because E and ds are parallel for the curved surface and E is constant throughout the curved surface. So we will simply write E into S equal to q by epsilon naught. The surface area of the cylindrical Gaussian surface is 2 pi r into L, isn't it? Where L is the length of the cylinder. The charge enclosed by this cylindrical Gaussian surface is clearly lambda L. That's because lambda is the charge per unit length of the straight line of charge and L is the length of the line of charge enclosed by the cylinder. When we further simplify this expression, the value of the electric field because of a straight line of charge is 1 by 2 pi epsilon naught into lambda by r. We had already derived this expression, by considering different elements on the straight line of charge and, calculating the electric field because of each element. But you can see that, calculating the electric field by using Gauss's law is so very simple.